Good morning, dear students. First of all, I would like to share an experience in front of you. In a strong windy day, if you have an umbrella, suddenly the umbrella caught wind and it will be inverted. Now the umbrella is called inverted umbrella. In our childhood, we had this type of experience. Maybe in a windy day or a rainy day, suddenly the umbrella is inverted out. So we have a term inversion. So this is an experience in your mind. So we can go to our new topic, nucleophilic substitution reaction, where I will teach you the term inversion. So you can assume with your experience of inverted umbrella. Okay. Now, nucleophilic substitution reaction. It is initiated by nucleophile. Nucleophiles are electron-rich species. For example, OH minus, Br minus, Cl minus. And we have some neutral nucleophile also. Water, H2 is a neutral nucleophile because of the two lone pairs of electron. And ammonia is another nucleophile. Okay, these are the list of nucleophiles. Just I tell you, these are the examples of nucleophiles. So this nucleophilic substitution reaction is initiated by nucleophile, and you know this is a substitution reaction. First of all, this nucleophilic substitution reaction is classified into two types. The first one is SN1 reaction. SN1 reaction. Second one is SN2 reaction. SN2 reaction. So SN1 and SN2 are the different types of nucleophilic substitution reaction. Now I would like to explain in front of you about the SN2 reaction and its mechanism. Okay. SN2 reaction. That is bimolecular nucleophilic substitution reaction. Okay. So students, why it is called bimolecular nucleophilic substitution reaction? Because it's very simple. The rate of reaction depends or proportional to the concentration of nucleophile. The concentration of nucleophile and the concentration of the substrate. Substrate means alkyl halide. Okay. Substrate. Yes. So in this reaction, the rate of the reaction depends both on the concentration of the nucleophile and a substrate or alkyl halide. We are taking alkyl halide as an example. Okay. So I will give you one simple example for SN2 reaction. Before giving the example, it involves only one step. It is a one-step reaction. The mechanism involves only one step. Okay. I can give you the best example is methyl chloride. Okay. CH3Cl. Methyl chloride or chloromethane. When the chloromethane is reacted with NaOH or KOH, they are bases, they will provide OH minus ions. Okay, OH minus ion is a very good nucleophile. So when we react it with NaOH or KOH, they will give OH minus ion. So the OH minus ion is coming to approach the substrate molecule CH3Cl. You know what happened? This OH minus ion will attack the CH3Cl, and what will happen? You will get CH3OH plus Cl minus. Why it is happened? Because OH minus is the approaching nucleophile. So when the nucleophile approaches this carbon, immediately the chlorine will leave. Dear students, the attacking nucleophile is coming to attack the carbon. At the same time, the leaving group is going to leave. Now the product is methanol. CH3OH is called a methanol. Okay. So in SN2 reaction, there is only one step. The simultaneous attacking of the nucleophile, at the same time the departure of the leaving group as halide ion is happened in that single step. And my dear students, now I'm going to teach you the mechanism behind SN2 reaction. Okay. In the mechanism of SN2 reaction, it involves only one step, single step. Okay. So here I put a nucleophile that is OH minus, and we have chloromethane HCH HCl. Before the product formation, there is a transition state, and that transition state is unstable and it cannot be isolated. We cannot be extracted that particular transition state. This is the transition state. Now the nucleophile is started the bond formation with the carbon, and the leaving group is ready to leave. That's why we are putting dotted line, because the bond formation begins, bond breaking begins, bond making begins, departure of halide ion begins. That's why here I put dotted lines, and I have to put the hydrogen also, H here, and another hydrogen here. Then here I have to put a solid words. Yes. Dear students, this straight line indicates the bond in this plane, okay? And this dashed line indicates, the bond away from the observer. And these solid words indicate the bond coming towards the observer. Okay. Now this is the transition state. Okay. This is a penta-coordinated transition state. That's why it is unstable and cannot be isolated. You know, the valency of carbon is 4. But in this transition state, carbon combined with 5 atoms. Instead of 4, carbon combined with 5 atoms, including OH. Okay, so one with hydrogen, chlorine, then with 2 hydrogen, then with OH. So this penta-coordinated carbon is highly unstable and it cannot exist for a long time. It is a very shortest time transition state. Okay, so it is unstable. We cannot isolate or we cannot extract it. And dear students, what will happen next? Next is the product formation. Okay, how it is formed. The OH will permanently combine with carbon. Okay, so you will get the product is formed. Just wait. Yes, here is the arrow mark. Then HOC. Here you have a hydrogen. Here you have a hydrogen. Here you have a hydrogen. Okay. Plus Cl minus. Okay. So dear students, what happened? Here you can assume that experience. I in the beginning of the class, I shared one experience of that inverted umbrella. Can you see the configuration? The three-dimensional arrangement of atoms around the carbon is called configuration. Here, can you see the configuration of carbon is inverted when the product is formed? See this product, the configuration is inverted. So, it involves the inversion of configuration. In SN2 mechanism, it involves the inversion of configuration, or it follows the, it involves the inversion of configuration. That is the stereochemistry of SN2 reaction. And I am repeating, this is a single step process, simultaneous attacking of the nucleophile and the departure of the leaving group as halide ion is happened here. There is a transition state which is unstable and which cannot be extracted or which cannot be isolated, and after the formation of transition state, immediately the product methanol is formed. This is called methanol. Okay, now methanol is formed and the leaving group left from the substrate molecule. And I told you one very important matter in this reaction, rate of reaction depends both the concentration of the nucleophile and the substrate molecule. Okay, here I would like to share one important information, that the order of reactivity, the reactivity order for tertiary, secondary and primary alkyl halide. Students, for primary alkyl halide, I can put this is a primary alkyl halide. This is a primary alkyl halide. Okay, this is a primary alkyl halide. Primary alkyl halide can show more reactivity towards SN2 reaction. There is a chemistry behind that. For that, I will give you three types of alkyl halide: primary, secondary and tertiary. Just wait. Students, now I discuss with you the order of reactivity of alkyl halide towards SN2 reaction. Okay, we have four types of alkyl halide. First of all, CH3Cl, chloromethane. Next, I am taking primary alkyl halide, that is CH3CH2Cl. CH3CH2Cl. This is a primary alkyl halide. Now I have one more example, secondary alkyl halide, that is CH3, CHCl. Okay. At last, we have CH3, CCl. Okay. This is chloromethane or methyl chloride, and this is chloroethane or ethyl chloride. This is the primary alkyl halide. This is primary alkyl halide. And this is secondary alkyl halide. Secondary alkyl halide. And it is tertiary alkyl halide. Tertiary alkyl halide. Okay. It is chloromethane or methyl chloride, and it is chloroethane. Chloroethane. This is isopropyl chloride. Isopropyl chloride. Okay. The last one is tertiary butyl chloride. Butyl chloride. Tertiary butyl chloride. Okay. And now I discuss with you the order of reactivity of alkyl halide towards SN2 reaction. It is very simple. The order is, dear students, it is very simple. The order is primary greater than secondary greater than tertiary. And you can put CH3Cl. Okay. CH3Cl greater than primary greater than secondary greater than tertiary. Okay. Why CH3Cl show more reactivity towards SN2 reaction? In CH3Cl, there are three small hydrogen, smallest hydrogen atoms. So, nucleophile can simply attack. Nucleophile can simply attack this carbon. Okay, but in the case of chloroethane, the order of reactivity of chloroethane as primary alkyl halide towards SN2 reaction, that value is 30. The rate of order is 30. But in the case of isopropyl chloride, the rate of order is 0.02. While in the case of tertiary, that is tertibutyl chloride, the attacking of nucleophile, that is order of reactivity, is 0. Why this is happened, my dear students? It is because of steric effect, steric hindrance. The bulky groups, methyl, these three methyl groups are bulky groups. It will make more steric hindrance or steric effect, or it will prevent the approaching of nucleophile, especially the tertiary. That's why the order is 0. The order of reactivity is 0, because in tertiary alkyl halide, the presence of three bulky methyl groups will not allow the approaching of nucleophile. So nucleophile cannot approach tertibutyl chloride. While in the case of isopropyl chloride, it's a secondary alkyl halide. There is two methyl group and a small hydrogen atom is there. So through this way, I will use one more ink. When nucleophile is coming to attack this way, it is possible because there is a small hydrogen. So it is possible. And in the case of CH3, CH2, Cl, there is only one methyl group, and the rest of the valence is filled by two hydrogens. So it is very easy to attack the nucleophile towards both the position. Okay, because bulky group only one methyl group is present. So steric effect have a very important role in the order of reactivity of alkyl halide towards SN2 reaction. Okay, students, today we have discussed nucleophilic substitution reaction. It is classified into two types, SN1 and SN2. Primarily, we discussed SN2 reaction. We discussed the mechanism also. And now we are discussing the order of reactivity of different alkyl halides. Then we found that CH3Cl have more reactivity towards SN2 reaction. After that, primary alkyl halide, then secondary, then tertiary. And what will make tertiary alkyl halide is does not show the reactivity towards SN2 reaction because of the steric effect. Because of the steric effect, steric hindrance or steric effect. It will hinder the approaching of the nucleophile. Okay, so this is with respect to SN2 reaction. And dear students, now we are going to discuss about SN1 reaction. Okay, SN1 reaction. And you don't forget the stereochemistry of this reaction is inversion of configuration. I already told that matter in the mechanism. It is followed by inversion of configuration. So what are the characteristics of SN2 reaction? It is a bimolecular nucleophilic substitution reaction, and it involves only one step, and there is no intermediate in this mechanism. There is no intermediate, only a transition state. It is not considered as the intermediate. And the order of reactivity of alkyl halide towards SN2 reaction is CH3Cl greater than primary, greater than secondary, greater than tertiary. And the stereochemistry of SN2 reaction is inversion of configuration. Okay, now my dear students, we are going to discuss about SN1 reaction. Okay, SN1 reaction. So dear students, now we are discussing SN1 reaction. SN1 reaction. Okay, so in nucleophilic substitution reaction, there is another mechanism, SN1 reaction. It is called unimolecular substitution reaction. Unimolecular substitution reaction. Why this is called unimolecular substitution reaction? Because the rate of the SN1 reaction only depends the concentration of the substrate. That is the concentration of the alkyl halide. Okay, so it depends. The rate of the reaction depends only on the concentration of the alkyl halide or substrate molecule, and it involves two steps. It is a two steps mechanism. Two steps are involved in SN1 reaction. The first step is formation of carbocation. And the second step is attacking of nucleophile. Attacking of nucleophile. So yes. So these are the two steps of the SN1 reaction. So listen all of you. In SN1 reaction, it is called unimolecular substitution reaction. The rate depends the concentration of the substrate molecule, and it involves two steps. The first step is formation of carbocation, and the second step is attacking of nucleophile. We can take one example for explaining SN1 reaction, that is tertiary butyl chloride. It's a tertiary alkyl halide. So tertiary butyl chloride is an example for the alkyl halide for SN1 reaction. Okay, so CH3, because it's a tertiary alkyl halide and one carbon, then I have to put one chlorine. Chlorine is the halogen. Okay, so this is the first step of the SN1 reaction, formation of carbocation. And my dear students, that is a reversible reaction. And it is the slow step of the SN1 reaction. And it is considered as the rate determining step of the SN1 reaction. So the formation of carbocation is the rate determining step of the SN1 reaction. And after the heterolytic fission, you will get, after the heterolysis or heterolytic fission, you will get the carbocation, that is tertiary-butyl carbocation, and Cl minus is left. Okay, and how the Cl minus is left from the alkyl halide or substrate molecule? It is because of the presence of polar protic solvent, that is called solvation. So solvation of halogen causes the leaving of halide ion. Okay, so polar protic solvent can enhance this reaction. So this is the first step of the SN1 reaction, formation of carbocation. And the examples of polar protic solvents are water, acetic acid, and methanol. These all are polar protic solvent, CH3OH. Since the H plus ion or hydrogen is bonded with highly electronegative element oxygen, that's why it is called a polar protic solvent. So my dear students, here I am giving you one more very important information. In polar protic solvent, the hydrogen, the H plus ion, that hydrogen is combined or directly attached with the highly electronegative element oxygen. That is why it is called a polar protic solvent. Only one hydrogen. In water also, in acetic acid, in methyl alcohol, everywhere you can see that hydrogen is attached with the highly electronegative element oxygen. So that is why it is called a polar protic solvent. So the heterolysis, first step is the heterolysis or heterolytic fission or formation of carbocation. Which is happened in the presence of polar protic solvent. So this is the first step of the polar protic solvent. And students, why I have taken tertiary butyl chloride as an example instead of taking methyl chloride or ethyl chloride or primary or secondary? Why I took tertiary butyl chloride as an example? Because the ease of formation of carbocation is more for tertiary butyl chloride. You know, tertiary carbocation is more stable than secondary carbocation, which is more stable than primary carbocation, which is more stable than CH3 plus ion, methyl carbocation. So in the case of alkyl halide, the SN1 reaction, first step formation of carbocation, that is immediately happened. That is happened very fastly for the tertiary butyl chloride. That's why I took tertiary butyl chloride as an example, and I will share that information while I'm discussing the order of reactivity of SN1 reaction. Please wait. So next, I have to discuss the second step of the SN1 reaction. Second step is the attacking of nucleophile. Okay, here the carbocation is formed. Next step is the attacking of nucleophile. Next step is the attacking of nucleophile. Okay. Yes. Second step is the attacking of nucleophile. Attacking of nucleophile. Okay. This is the second step. So carbocation is ready for nucleophile. Nucleophile is nucleus loving. Electron deficient centers loving. So nucleus are waiting the carbocation. Students, in carbocation, can you see a positively charged carbon that is electron deficient? So nucleus is ready to attack that carbocation. So that carbocation I'm writing here CH3 C plus. This is the tertiary butyl carbocation. Tertiary butyl carbocation. Okay. So in this case, the tertiary butyl carbocation is attacked by the nucleophile. We can take OH minus ion as an example for the nucleophile. So the hydroxyl ion or hydroxide ion is easily coming to approach the carbocation. So this is the way how the nucleophile is attacking the carbocation, and you will get a tertiary butyl alcohol CH3 COH. And students, it is a very fast step. So it is not the rate determining step. The rate determining step is the first step, that is the formation of carbocation, because since it is a slow step, it is used to calculate the rate determining step. Okay. So this is the second step of the mechanism of the SN1 reaction. So here I discussed with you the mechanism also. The first step is the formation of carbocation, and the second step is the attacking of nucleophile. These are the very simple mechanism behind the SN1 reaction. Now I am going to discuss with you the name of the product also. Tert-butyl alcohol. Tert-butyl alcohol. Tert-butyl alcohol. Okay, tertiary butyl alcohol, or it is called 2-methyl propane 2-ol. 2-methyl propane 2-ol. That is the UPSC name. Okay, so this is the two steps involving the mechanism of the SN1 reaction. Now let us discuss, my dear students, let us discuss the order of reactivity of SN1 reaction. Order of reactivity of SN1 reaction for alkyl halide. I already discussed one important matter. Tertiary carbocation is more stable than secondary carbocation, which is more stable than primary carbocation, which is more stable than methyl carbocation. So once the carbocation is formed easily, then nucleophile will come to approach the carbocation. So as we know, tertiary alkyl halide gives tertiary carbocation, which is highly stable. So the ease of formation of tertiary carbocation will be happened quickly. So the attacking of nucleophile will be happened quickly. Okay, so the order of reactivity of SN1 reaction is tertiary greater than secondary greater than primary greater than CH3 plus. Why? Because of the first step, that is the rate determining step, formation of carbocation, where you can see tertibutyl carbocation is easily formed because of its stability. Okay, then we have secondary, then we have primary, then we have methyl carbocation. So this is the order of reactivity of alkyl halide towards SN1 reaction. So I can write like this also: CH3 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 C Cl greater than CH3 CH3 CHCl greater than CH3 CH2 Cl greater than CH3 Cl. Okay, because this methyl carbocation is given by methyl chloride or chloromethane. So this is the order of reactivity of various alkyl halide towards SN1 reaction. Okay, now let us discuss the stereochemistry of the SN1 reaction. Stereochemistry of the SN1 reaction. Very interesting stereochemistry is present in the case of SN1 reaction. Okay, so please listen. I will take one example for you. We can take that tertiary butyl carbocation, that is tertiary butyl chloride. So when we use tertiary butyl chloride, the first step is the formation of tertiary butyl carbocation, that is CH3, 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 C plus. Actually, dear students, the hybridization of tertiary butyl carbocation or any carbocation is sp2 hybridization. sp2 hybridization, and you know the shape of sp2 hybridized carbocation is planar shape. It has planar shape. So here I am drawing the planar shape of the sp2 hybridized tertiary butyl carbocation, that is CH3 C CH3 CH3. Here you have the positive charge. So it is exists in a plane. It has a planar shape. So there is two chance for the nucleophile to attack the carbocation through the backside attack. Backside attack is possible, and a front side attack is also possible. Front side attack is also possible. Okay, so nucleophile is coming to attack from the backside like this. This is also happen, and nucleophile can also approach the carbocation, tertiary butyl carbocation or secondary propyl carbocation, that is isopropyl carbocation or primary ethyl carbocation or simply methyl carbocation. Any carbocation doesn't matter, because of the planar shape and sp2 hybridization, the nucleophile can attack from the back side or the front side. Okay, so the stereochemistry explains there is two chances. Initially, the structure of the tertibutyl chloride was like this: CH3, CH3, CH3. I can put a straight line and a dotted line, that is dotted words, and I can put a solid words also. Okay, so a straight line indicates the carbon CH3 bond, that is straight line, is in a plane of paper, and this dotted line indicates or dashed line indicates away from the observer, and the solid words indicates towards the observer. So this is tertiary butyl chloride, and this is the another structure. So why I put this structure also? For the explanation of the stereochemistry. Once the nucleophile is attacking from the back side, what will happen? If the nucleophile is OH minus, what will happen, my dear students? The structure will be HOC CH3 CH3 CH3. Okay, so can you see inversion of configuration is happened in the first case. Once the nucleophile is attacked towards the backside, inversion of configuration is happened. Like an inverted umbrella, the configuration has been changed. Once the nucleophile is attacking towards the front side, what will happen? Towards the front side, what will happen? You will get a product. That is nucleophiles. In this case also nucleophile we are selecting as OH minus ion. OH minus ion. So once a nucleophile is attacking this tertiary butyl carbocation from the front side, what will happen? What will be the product? The product will be CH3, 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 COH. Okay. Dear students, look this structure and this structure. Can you see any difference in the configuration? No difference. Configuration is retained. Configuration is preserved. So once the nucleophile is attacked from the front side, the configuration is retained or preserved. There is no change in the configuration. It is called retention of configuration. So the retention of configuration is happened. But once the nucleophile is attacking on the back side, what will happen? Inversion of configuration will be happened. So there is a chance of 50-50 percentage. 50-50 percentage is a chance for the attacking of the nucleophile. One from the back side and one from the front side. I will also explain the stereochemistry of the SN1 reaction by taking a chiral carbon. Okay, please wait. Chiral carbon. Actually, this is not a chiral carbon because chiral carbon should contain different types of the alkyl group. Here in the tertiary butyl chloride, I have taken 3 methyl group. They are the same 3 groups, so the carbon is not chiral, it is achiral. So for explaining the stereochemistry of the SN1 reaction, already I explained the retention of configuration and inversion of configuration. And I can also explain the same mechanism by taking a chiral carbon. Before that, I can say the chance of 50-50 retention of configuration and inversion of configuration. If the carbon is chiral carbon, you will get enantiomers or stereoisomers as the product, and you will get a racemic mixture also. So simply we can say in SN1 reaction, the during the two chance backside attack and front side attack, there is two type of configuration change. That is first one inversion of configuration, second one is retention of configuration. Totally you will get a racemization. For explaining racemization, I will take a chiral carbon containing compound. Just wait. The tertibutyl chloride containing carbon is not a chiral. That's why I would like to take one more example for the same SN1 reaction stereochemistry explanation. So please wait. Okay, dear students, here I have the example 2-bromo butane. 2-bromo butane. Okay, 2-bromo butane structure is CH3 C. Here you have Br. Here you have CH3 CH2. Okay, and here you have a hydrogen atom also. Okay. So CH3, CH, CH2, CH3. It is called a 2-bromo butane. And dear students, this is a chiral carbon. Since you can see here a methyl group, here an ethyl group, here a hydrogen, here a bromine. So for following the SN1 mechanism, first of all a carbocation is formed. So the carbocation after the heterolysis, it will be CH3, C, CH3, CH2, H. This is the carbocation. It is sp2 hybridized and planar shape. Okay, next step is the attacking of the nucleophile. Okay, so for 2-bromobutane, the carbocation is secondary butyl carbocation. This carbocation is called a secondary butyl carbocation. Secondary butyl carbocation. Next is the attacking of the nucleophile. Attacking of the nucleophile. Attacking of the nucleophile. Okay, attacking of the nucleophile. So secondary butyl carbocation is here, CH3 C plus CH3 CH2 H. Okay, so dear students, there is a there is a chance of backside attack for the nucleophile OH minus, and there is a chance of front side attack also. Why I have taken the second example also? Because the first example was tetrabutyl chloride, that was achiral, because of the same 3-methyl group. Now I have taken a secondary alkyl halide 2-bromobutane. It will also show the SN1 reaction in the presence of a polar protic solvent. First of all, it will give after the heterolysis or heterolytic fission, it will give secondary butyl carbocation, and after that attacking of nucleophile will be happened for two sides, back side and front side. Once it is attacking from the back side, it will be inversion of configuration. Once the nucleophile attacks from the front side, it will be retention of configuration. Okay, so retention of configuration will be happened. Retention of configuration will be happened once the nucleophile attacks from the front side. And when the nucleophile attacks the back side, both possibilities are there. Back side, what will happen? Inversion of configuration will be happened. Inversion of configuration will be happened. Okay, so there is a 50-50 chance. 50-50 chance. Okay, so you know, dear students, the formed product are the formed product should be secondary butyl carbocation. From the secondary butyl carbocation, you will get the product secondary butyl alcohol. You will get. Okay, that product is stereoisomers or enantiomers. Enantiomers are stereoisomers, and they have non-superimposable mirror images. Okay, so you will get two exact two types of enantiomers you will get because of the inversion of configuration and retention of configuration. You have a chance of getting 50-50. Once you get the 50-50 chance or 50-50 product of the result of inversion of configuration and retention of configuration, your product should be a racemic mixture. Your product should be a racemic mixture. Racemic mixture. Okay, so the formation of product contains two types of enantiomers. Once the enantiomers attains a percentage of 50-50, that mixture of enantiomers are called a racemic mixture, because it will rotate the plane polarized relate into right and left equally and oppositely. 50% of the product will rotate the plane polarized relate into right direction. 50% of the product will be rotated the plane polarized relate into left direction, dextro-rotatory and levo-rotatory. That's why the product should contain two types of enantiomers in a equal and opposite way. So this is called a racemic mixture. And the stereochemistry of SN1 reaction, finally it is racemization. Okay, so why the stereochemistry of SN1 reaction is racemization? Because of the planar shaped tertiary or secondary butyl carbocation. If it is a chiral carbon containing compounds, you have two chance of configuration, that is inversion of configuration and retention of configuration. Both will give you a mixture of enantiomers. They are stereoisomers which are non-superimposable mirror images, and once that 50-50 percentage is formed, it is called a racemic mixture. It is optically inactive. That once you get a racemic mixture in this case, then the entire mixture of product, that product should be optically inactive, and both are enantiomers. Enantiomers have the same physical properties. Enantiomers have same melting point, boiling point, refractive index, solubility, everything is same. So but only one difference is, once one enantiomer rotating the plane polarized light into right direction, one enantiomer rotate the plane polarized light into left direction. That is the only one difference between these two enantiomers, and the equal proportion, 50-50 percentage proportion of that enantiomers is called a racemic mixture, and the formation of racemic mixture from enantiomer, it is called racemization. Racemization is the conversion of enantiomer into racemic mixture, okay, and they are optically inactive. You should know what is plane polarized light. Light vibrate in all directions. If we restrict the rotation of light into one plane by using a nickel prism, now the light is called plane polarized light. Once a compound is coming to rotate the plane polarized light, or a solution is coming to rotate, or when we pass the plane polarized light through a solution, and the solution rotates the plane polarized light into right or left, clockwise or anti-clockwise, that phenomena of that solution is called optical activity. Enantiomer can rotate the light. Enantiomers have the optical activity, and the optical activity is only because of the chiral carbon. Chiral carbon is nothing but the carbon having four different groups. A tetrahedral carbon having four different groups, methyl, hydrogen, ethyl, or any other group. Such type of alkyl halide have chiral carbon. Such chiral carbon can initiate the optical activity. So here I discussed with you nucleophilic substitution reaction. It involves it involves two type of mechanism. First of all SN2, then SN1. SN2 means bimolecular nucleophilic substitution. SN1 means unimolecular nucleophilic substitution. In SN2 there is only one step, but in SN1 there is two steps. In SN1, the first step is formation of carbocation, and the attacking of nucleophile is the second step. Okay. Regarding to SN2 mechanism or SN2 reaction, we can say some points. The first point is, it is a single step process, and there is no intermediate is formed in SN2 mechanism. And once the nucleophile is attacked, then the departure of the leaving group as halide ion is happened, and the order of reactivity of alkyl halide towards SN2 reaction is primary greater than, secondary greater than, tertiary. Okay. In the case of SN1 reaction mechanism, it involves two steps. The first step is formation of carbocation, and the second step is attacking of nucleophile. And the first step is the rate determining step. It is a slow step. There is a intermediate of formation of carbocation in SN1, and the order of reactivity of SN1 reaction is tertiary greater than, secondary greater than, primary. That is the chemistry of both SN1 and SN2 reaction. And you, my dear students, you don't forget, there is no intermediate in SN2 reaction. There is only a transition state which is highly unstable and cannot be isolated. But in the SN1 mechanism, there is a intermediate of carbocation. Okay. At last, the stereochemistry. I told you, I discussed that matter in SN2 reaction mechanism. The stereochemistry is inversion of configuration. I shared with you my experience of inverter umbrella when I was in the childhood. I faced that experience once I went through the paddy field. At that time, a storm came, wind came, strong wind came. Then my umbrella was inverted, turned inside out. I sincerely I think that I assume that mechanism during the discussion of the SN2 reaction, that is inversion of configuration. So SN2 reaction follows the stereochemistry of complete inversion of configuration, while in the case of SN1 reaction the stereochemistry is just racemization. Only one condition, the carbon should be chiral carbon, so you will get enantiomers, two types of enantiomers, and if you get a chance of 50-50 percentage product which is enantiomers, or which are optically active but they are non-superimposable mirror images, and once they reach their proportion of 50-50 they are called a racemic mixture. The racemic mixture is optically inactive because the 50% one enantiomer optical activity is dextro, it will be cancelled by the rest of the 50% enantiomer, that is levo. So both are cancelled, both optical activities cancel each other, hence the racemic mixture is optically inactive. So my dear students, SN1 reaction follows racemization because of the two probability of the attacking of the nucleophile from the back side and front side, from the back side and front side. Okay, these are the things regarding to nucleophilic substitution reaction. So thank you my dear students, thank you so much.